All right, if y'all would go ahead, pass that folder around. Be sure you... All right. You're welcome to have your homework back. But when you take your homework out, if you take out the whole thing, please put it back where you got it from. Because then everybody else there at the end of the class, I can always tell. It's Emiraj, Imran, Emrike, and Imrup can't find their homework because you stuck it in the Z's. Stick it back where it belongs. Secondly, I notice that I'm collecting a lot of homework from a Mr. Name ? I just put them under N. So if you're not getting your homework back, your mom didn't call you that, but that's what's listed on the thing as it comes back from the grader. All right, we were working on shear and moment diagrams for statically determinate structures. Mr. Munson? Mr. Munson? Are you ready to begin? He is not going to tell you her telephone number, no matter how you beg him there, so you might as well get information from this direction. That is a statically indeterminate structure. What I'm going to end up having to do is to remove enough redundance. What I'm going to have to do is lie such that it becomes a statically determinate structure. Find out how much the structure deforms at the point where you removed an extra redundant or an extra reaction. Admit to the world that that deflection was undesired and must go away. Put a reaction back where that reaction was and negate that deflection so that you end up with the proper deflection at each point. First off, a pin would cause two forces, an unknown A vertical and an unknown A horizontal. I already see what's wrong with this. Some jerk went in there and put a support at B. Had he not put the support at B, it would have been a nice, straightforward, simply supported beam with a load on it, and I could get a shear and a bending moment diagram for it. Having the moment diagram and the shear diagram, I could design the beam, and I could collect my fee. But right now, I'm not destined to get an answer. There is a reaction at B, and there is a reaction at C. There are 4 unknown reactions on that structure, and you have been given 3 equations of statics, as have we all, in 2 dimensions. And therefore, it is statically indeterminate to the first degree. Write down one of them. The rest of them I'll just put 3rd degree, 5th degree, whatever it is. Now all you have to do is extract a reaction of your choice. Please don't make the structure unstable when you release or remove one of the unknown forces. For example, if you take off A horizontal, you have a roller, You have a roller. You have a roller. You have a new force. This wouldn't necessarily be a vertical anymore. And you have a potential reaction. You have a potential reaction. And sadly, when you try summing forces horizontal, it's not equal to zero. Well, it may be equal to zero, but the structure is unstable because it is not constrained in the x direction. So that's not an acceptable take a reaction loose. So instead, I will leave a horizontal on there. Now, I really can't call these the same thing. I'm just going to have to leave names off of them because once you start removing reactions, obviously, all of the other reactions will change. So this is a vertical. This is, I guess a better name with that would be consistent. Now that I'm going to take one of those things loose, this won't be a vertical anymore. It's going to have a new name, and it'll be a new value. And I will take out the middle support, turning it back into a regular old beam, a regular cantilever beam with some forces on it. And it will do this unfortunate thing. It will deflect at B. And that isn't what you wanted in the first place. What you wanted in the first place was for this structure to deflect. And then you wanted it to go back through B so that it didn't have any deflection. And then deflect perhaps something like that. I don't know who's going to win that game. It could be this will push down so hard that this force will actually go upwards. Possible. Could be because this is concentrated. It'll push so hard down, this will actually lift up. Possible. But generally speaking, this has to be here, and this has to be there, and that has to be there. You'll notice that there's no slope predicted. I don't know what it is. Could be zero, but it's not zero except just by chance. In other words, if this pushes down and that pushes down so horribly that it raises this up, could be the rotation on the left end is zero. But that's not required because this is a pin. This would be deflection at B, which you should be able to solve for. There are various and sundry ways to do that, one of which is you can look up in tables. You could go to a set of tables and find a 30-foot long pin beam with a load only on the left half, and he'll tell you how much that deflects down. Then you could go look up in another page in that same book, put a 15-kip load at the 5-foot, oh, that's 50 feet, isn't it? Nope, 25, 35, it's 45 feet long. You put the load at the 5-foot mark on a 45-foot long beam, and you can solve for the deflection in the middle, or at the 25-foot mark. Then you would add this deflection from the tables plus that deflection to the tables. That would give you the deflection at B. That's one way to do it. There are other ways. There are better ways. That is a sad situation. You would have to say that this is equal to this plus, then you would come back in here and you would put a reaction at B. It would cause the beam to go up like that. You'll notice that at the point of load is not necessarily the point of maximum deflection. In fact, it would not be, although this would occur reasonably close. And that would be, perhaps this would be delta B1 due to the first set of loads. You might call that delta B2 due to the second set of loads. Once we get into the book, they'll have a naming convention that we'll use. You would say that this is equal to that plus that. You would make this number right here perfectly such that however far this goes down, this goes back up. Being able now to solve for B vertical, you would list A vertical, a B vertical, C vertical, and you start drawing a shear in a moment diagram. If you just want a shear in a moment diagram, one of you in here mentioned, can you just go all the way from end to end? Yes, you can. You just consider that's just like a load. If you're going to find deflections at different points, you may want to break it up into ranges, and we'll talk about that later. All right, so what I'm going to do now is I'm going to continue. That one didn't work. That pair right there, it worked nicely. Now then, instead of that, I'm going to show you the person who took this reaction loose. They left this one, and they left this one. There's a reaction here. There's a reaction there. There's a load here. There's a load here. And this is why we're learning or practicing on how to draw the deflected diagram. My guess is that that's going to push that down a little. My guess is this thing here is going to roll this like crazy. And I'm going to connect it kind of like that. Whether or not that really goes down or if this horrible moment over here raises the load up, I don't know. But you'll notice that my structure to analyze has, I'm going to leave this reaction on there, has three unknowns, and I have three equations of statics, and I ought to be able to solve for all the reactions. I see the problem. You say, that ain't right, that ain't right. You're certainly true, that's not right. There's the deflection at A due to the first set of loads that shouldn't be there. We would have to get rid of it by taking the original structure and putting, I don't know what, a reaction at A on it, thereby bending this thing up. And it would be your job to tweak this number such that this displacement up was identically equal to this displacement down. And a third possibility would be that the structure be modified for analysis by taking the right-hand reaction off. That would leave you with a vertical force, a horizontal force. I hesitate to call it A vertical because you'll think it's this guy, and it's not. And a force at B, and a load like this, and a load like that. I can put this down. This is still 3 kips per foot, and this is still 15 kips. And I will draw you the deflected shape of the structure. I think it looks like this. It may not. It may be that that doesn't go so far down. And it may be that this bends down like that. This last little piece is straight, whatever it is, because there's no moment past that point. And again, you would say the problem is now at C. So you would have a deflection at C due to the first set of loads. If you guess it's up, once you solve it, if it turns out to be down, you'll get a minus number, and you'll know it actually deflected too low below the zero deflection point. Then your, what they call a complementary solution, would come in with a reaction at C causing this kind of deflected shape. And it would be your job to pick R sub C so it just exactly, perfectly cancels out delta C1. So there are 3 structures there that you could use. Well, there's 4 that you could use because you have 4 reactions. But one of them is not going to work because you don't have equilibrium in the horizontal direction. Even if there are no loads in the horizontal directions, one of your equations will be some force is horizontal, and even though there are no loads, and if you say I don't need some force is horizontal, you've lost that equation. If you need it, you can use it. If you don't need it, well, in effect, you've already used it. Davis, how many reactions? There are indeed. There's a D horizontal, whether it's used or not. If it's 0, that's fine. Right now, nobody's putting on their brakes. If somebody was to slam on their brakes while this traffic is flowing across the bridge, then D horizontal will come into play. And there's a D vertical, and there's a C vertical, and there's a B vertical, and there's an A vertical. Just start taking things loose until it becomes a nice, plain old, simply supported beam, or an overhanging cantilever beam, your choice. The most obvious thing usually is you just take off B vertical and C vertical so that you have a structure that looks like this. And you put all the loads on it. And it sadly deflects like this, causing some deflection at B due to the first loads, and some deflection at C due to the first loads. And then it would be your job to come and make the thing go back up to 0 at those 2 points. In other words, you need to be able to draw the deflected shape. My guess is it looks kind of like this. Whoops, that doesn't look like that. You see what happens? I was getting to a point and I couldn't get back through this pin. That's my guess as to how it would deflect. And I think that's almost guaranteed. When this span goes down, this end rolls and it pushes this span up. When this pushes down, this end rolls and pushes that span up. And so unlike some of these here, where depending on the magnitude of the loads and the size of the beams and the distances, it could go up, could go down, that one's pretty much guaranteed. Then you would come back, you would have a beam that you would put a load at B. It would cause the thing to deflect up kind of like that. You'll notice that the maximum deflection does not occur at the load. It actually doesn't occur at the middle either. It usually occurs somewhere between the middle and the load. Not that I care, because nobody has constrained the beam at that point, so I don't care what it deflects. And I would call that perhaps, I don't know, maybe a little delta at B due to the second loads. Maybe a deflection at C due to the second loads. Big delta is okay. Big delta is usually a symbol for real loads. They usually kind of reserve that for the real loads caused these. And of course, these are real loads, but you will find that we don't put R sub B on here. We usually put a 1. And then we jack the 1 up to the proper number. So if there was a 1 on here to try and find out what's going on, a lot of times they use the lowercase delta. Then you'd come back. You would put a reaction at C truth is you'll put a 1 pound load there and find out how much a 1 pound load kicks it up, and then raise it up till R sub C is appropriate. And it causes deflections that look kind of like this. I might call that delta B due to the third set of loads, delta at C due to the third set of loads. And then I would write a set of equations to make this thing work out. First, delta B1 has to be canceled by this number and that number. In other words, this minus this plus that is equal to my final desired deflection equals 0. So you'd basically have an equation that says delta B1, which you could solve for because it's statically determinate, and that's minus, you'd say plus delta B2 plus delta B3, and when all is said and done, you'd want it to be 0. And of course, this has got an R sub B in it, and this has got an R sub C in it. And so when you write this one equation, there'll be two unknowns in one equation, so you're still not there. Then at this point, you would say minus delta C1 plus delta C due to the second set of loads plus delta C to the third set of loads comes out 0. This would also have an RB and an RC in it. You'd have two equations and two unknowns. Crawford, you got that? You understand?
Yep.
Are you sure? It's supposed to equal to 0. All right, just checking on you there. Crawford, how many unknowns? Excuse me, I'm just tinkering while you're thinking there. How many?
5.
5 unknowns, that's correct. Because this shows embedded, fixed at the wall, which means there's 3 possible reactions to that. Then we have a reaction at B. This would be A vertical, A horizontal, moment at A. This would be the reaction at B, and this would be the reaction at C. G, where's G today? G. Good morning, G. What would you personally turn this into? That's what I'd do. Just turn it into a cantilever. In other words, you would take off these 2 supports. Here I'm going to show you the real deflected structure. Comes out of the wall, not moving up and down in the Y direction. Comes out of the wall, not moving to the left or right. Comes out of the wall with no slope. Then it starts to slope, and then it is constrained. It is forced to go back through the pin at B. Who's going to win this battle? I don't know. It might look like that for all I know. The only things I know is no X, no Y, no theta. No Y deflection, no Y deflection. That's truth. G says he will turn it into a cantilever beam. I have some sad news for you, Mr. G. When you put the loads on there, they will cause the cantilever beam to distort in an undesired direction. There will be some deflection at A due to the real loads. There will be, that's B. There will be some deflection at B due to the real loads. And there will be some deflection at, how come nobody hollered? Yeah, well, you got to be careful because I'll walk right up to the cliff and like a lemming, you'll go on over and I'll still be on the edge. Dismute. Why wasn't I happy with that? Wait a minute. Maybe I could be happy with that. No, yeah. No, I could be happy with that, can't I? It looked so ugly, I just didn't believe it. But you know, I didn't break any laws. I made sure there was no deflection there, and I made sure there was no deflection there. Why you started solving for this deflection, I don't know, because it is unconstrained. Nobody has told you it has to be something special. So my real mistake started when I drew that. The minute I drew that, I thought, uh-oh, there's not supposed to be zero deflection there, and so I thought I had my curve wrong. Curve is okay. Curve is possible. But I don't need the deflection there. This is the problem. There is a deflection at C due to the real loads. I hope you realize, and we will do this, we won't use the method that you used in 305, but you should be able to solve for the deflection at B due to these two loads and the deflection at C due to these two loads. The quickest and easiest, or one of the quickest and easiest ways, would be to look it up in a book. If you just have very basic deflection tables, he may not show you how much deflection you get out on the end of a uniformly loaded cantilever beam when it's not loaded all the way. You might have to go get a more complete book. For example, the LRFD, AISC LRFD book has hundreds and hundreds of these things. That's what you'll use in 446 steel design. Then you will come back and you'll put a unit load right here, and it will kick the cantilever beam up. Good morning. You're early. Well, I mean, for you. You're usually not here quite so early. But that's okay. You always give me good answers, so I have no complaint. And let me move that a little bit. Because it ought to go right at point B. And it will cause a deflection at B because you put a load at B. And it will cause a deflection at C because you put a unit load at B. And you say, well, you don't have a prayer with a weenie old 1 in there. You're right. 4 things are over with. I'm going to have to go ahead and multiply that 1 times the reaction at B, at which time this reaction will increase, and at which time this displacement will increase. How much? R sub B. It's probably going to be 37.2. Well, you put a 1 on there, you got some good numbers to begin with. They're just off by 37.2. Next, I'll show you the cantilever beam with a unit load placed out at the end at point C. It will cause the beam to deflect. This picture is wrong. I mean, it's not so wrong that you lose points, but you'll notice how it's curved, 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 curved. The truth of the matter is, at this point, the beam truly would no longer bend. It would remain straight. The reason is the 1 pound has no bending moment here. 1 times 1 foot, 1 times 2 foot, 1 times 8 foot, 1 times 10 foot, 1 times 12 foot. That's bent. But on the free end of the cantilever, there is no force. Therefore, it's not bent. Therefore, that line, strictly speaking, ought to be straight. This deflection right here, Plumber caught him, not here. Huerta, what is this guy's name? Looking at what I call these people here, noticing that this deflection is at point B, was caused by somebody at C. What's his name? A little louder. Yes. See, this guy's deflection right here is delta at B, because that's where we're at, caused because you put a force at B, that one there. This guy's name, how far this cantilever moved up, that's the deflection at point C, because that's where we're now standing, because you put a force at B. So what's his name? What's his name? It is a delta, that's correct. At BC, that is correct. Now, if you don't see that, you're behind her. That's the deflection caused at point B because somebody put a unit load at C. And I'll admit to you that before things are over with, that 1's not going to do the job. You're going to have to come put R sub C on there, which means that that deflection will be R sub C, delta BC. Carol? What is this guy right here without the R on it yet? It's a little delta. It is at C because there's a load at C. That is correct. And then, of course, when you up this 1 to a R sub C, which is the final answer, then it will be times R sub C. And now then, we finally got to the point where I can write you an equation that really makes a lot of sense. Minus delta B due to the real loads plus delta at B due to a unit load at B times the real reaction at B plus the deflection at B due to a unit load at C times the reaction at C is equal to whatever the deflection is. Doesn't have to be 0. The guy could say that we anticipate that this pile, this support, will settle a 1/2 inch. I'll just stick a 1/2 in there. Second equation would say minus the deflection at point C due to the real loads plus delta CB R sub B plus delta CC R sub C is equal to 0. Each of those numbers you really could do with nothing but your 305 work. You would find this deflection out of the tables on a cantilever beam, uniformly loaded all the way to the end. Oh no, we got to have this one too. So you'd have to find a cantilever beam that's at least that long, and then find out with 800 pounds per foot how far it goes down, and with another 4,000 pounds on the end how far it goes down. And the same thing here. Then here you'd go back to your cantilever beam. You'd take off the uniform load and the concentrated load. You'd put a unit load at the point where you got problems, and you would cause it to go up. What is this number right here? If I find it before you do, pop quiz. I'm asking the equation for the deflection at this point right here due to a unit load. And I haven't said what you get if you find it first. PL over AE is correct for axially loaded rod. But this is not axially loaded. This is transversely loaded. And the reason that we all have about the same chance of getting the answers, I don't know where his deflection tables are. Oh, I just found them. They're on the front of the book. And it's a cantilever beam, and it's case 4. And the answer is PL cubed over 3EI. And you say, well, wait a minute. That's not what my beam looks like. My beam looks like this. It's 12 and 10 and 10. Well, just this little piece of your beam isn't. In other words, that little piece of your beam there is 12 feet long, and it's a cantilever beam, and it's got a deflection on it. Now, your tables would not give you this deflection. Most of the books actually would. Most of the books will tell you the slope on the end of the cantilever beam, and they'll give you an equation for theta. And knowing that this is a straight line, you could find out how much higher it goes just due to that slope. But I'm not going to belabor that point. I'll admit to you 100% there's better ways to find these deflections, as many of them as we need, than looking in tables and piecing together the slope on the end of a cantilever beam and how far does it stick out there and add it to this number. There are better ways, and we'll cover them. But this is important. Now then, the interesting thing is you don't have to pick the initial statically determinate beam that I picked. As you just saw from the other ones we did, there are other choices. None of them I don't think are as good as that one, but they'll work. Here's the beam. I have 1, 2, 3, 4, 5 unknowns. I had to remove 2. Yes, ma'am. Oh, I don't know. It's case 4. Thank you. No. You're talking about these here? See, the deflection, if it's distributed, is quite a bit different than if it's concentrated. If it's distributed, it's WL fourth over 8EI. I'm sorry? Oh, it has to be over the whole thing. That's correct. Otherwise, if it was over halfway, then you get a different answer again. And we don't have that answer listed in the book, in your book. All right, so I had to remove 2 things, and I removed, in fact, I didn't do it. Somebody else did it for me, but the most obvious thing was to make it into a cantilever beam. What I could do is I could leave this force on there so nobody can steal it. Nobody can roll it right and left. And then I just take off this left moment and this left reaction and put a support here and a support here. And I'm going to have to leave a horizontal on there, even though it's not used for anything.
Why are you doing that?
Well, I don't have a good answer for that question. Why am I doing this after I already did a perfectly good thing that couldn't be any nicer or simpler? Because I'm the prof. That's my job. See if I can confuse you.
But what are we trying to...
I'm trying to make a statically determinate and stable structure out of this thing that doesn't look like the good one. The way we got the statically stable structure that was statically determinate so that we could get shear, moment, and deflections was we had to remove 2 supports because it has got 5 supports on there, and you only got, oh, you weren't here then, but you get 5 equations of statics, okay? So now what I've done is I have chosen to remove M sub A. It's gone, it's history, it's out of here, you never saw it, and I have removed A vertical. I have left A horizontal, and I just hesitate to call that R sub B, you know, because it's not this RB, but it's some kind of a force at B. I just call it.
When you're trying to make a statically determinate structure out of a statically indeterminate one,
Correct.
you're actually removing reactions, not supports.
Well, I don't know. They kind of always thought they were the same thing, but in other words, a reaction is a reaction to a load, and it's there because there's a support.
But sometimes, like in this case, you have a support, and you can get rid of 2 reactions. You know, because you have 3 reactions because of that support.
Well, I do, but I didn't remove one. If I take this one loose, then you can roll it down the road, and I can't have that. It's too expensive.
So you didn't actually remove the support. Because had you removed the support, you
I removed the horizontal ability of this support. I removed the horizontal support. I'm sorry, the vertical support, and I removed the moment support. Are you just into semantics? Is that, you want to call those reactions?
like good procedure to go about.
This is a good procedure. It really is. I've used it for 50 years. It works like a champ. Well, I don't care what you call them. I really will. I'll try and call them. You want to call them support reactions?
Well, you know, if I were to get rid of that support, I would think of it as like the support is gone.
Okay. Well, no, that is not permitted. If that's what you're thinking, no, I cannot remove that support and have nothing there, because then it'll roll. All right. Now then, these 2 reactions, we'll leave them on there, and we'll leave the supports on there too. And I will show you what you caused. You did it. I didn't do it. I wanted this one back here. Your beam will now sadly do this. I'm not going to bother showing the loads. You see what happened. You will now get an unfortunate thing called the deflection. They usually give it a cap symbol to show it's due to the real loads. At A, due to the real loads. I'm not sure why we have to say that twice, probably don't. And you will get a theta at A due to the real loads. Those are the 2 inconsistencies that you have caused by your choice of removing reactions. Lane, did you get that? You figure that? Do you see that? Here, let me show you. You know, maybe I'll make it a little thicker. It'll become more obvious. It's a piece of steel. You'll notice it still meets the constraints. No deflection at B, no deflection at E. You'll notice that when you did it his way, you ended up with 2 problems. A deflection at B due to the real loads and a deflection at C due to the real loads, which you had to come back in and get rid of. Same thing has happened here. 2 problems have occurred. Number 1, the left end of your beam went down, naughty, naughty, and it rolled. That's not good. Therefore, your complementary solution would be to come back to the original beam and put a vertical force on it, A vertical, which would cause this kind of deflection. Now, I'm hoping you're seeing how I'm doing these deflections and that you can do them too, because you're going to need to. I mean, if you can't see these deflections and give them names, you got a real problem solving these problems. And that force would cause, here, let me do this, no fair, no fair. Let me put a 1 on there first, because that's what we always do. That would cause a deflection at A due to a unit load at A. We'll come back in and we'll multiply this times R sub A later. It would also cause an angle. What is the symbol for a little theta? Anybody know the Greek symbol for a little theta? I forget what it is. We'll give it this symbol here till I can remember what it is. It's got to have a different name to it because it's due to a unit load at A because you put a unit load at A. Okay? Then the next thing, you've got to come back and admit that there was a moment on the end of this beam. So here is the beam. Here is a 1. This will be like 1 kip, 1 pound. It really will have no units because the units will come when you multiply it times the reaction at A, times the reaction at A, times the reaction at A. That's where the units come from. This guy doesn't have any units. That's why this isn't a 1 kip, really. It's just a 1. Then when you do this, the beam will bend kind of like this. And there will be, let me move the 1 so I got room for my deflections. I'll put it down there. And that will cause some, what am I going to call this now? It's going to cause some deflection at A due to the moment at A. Let me put a little m sub A to distinguish it from this one. This one's due to a concentrated load. This one's due to a unit moment. And you'll have some rotation at the end. Darned if I know. But we'll just still call it a theta. And it will be at A, and it will be due to a unit moment at A. The truth is this is times m sub A, so this one will be times m sub A, and this one will be times m sub A. And the equations will work out just like before. Your first equation will say, I don't want this to move down, because in the original case, it didn't move down. And so you would say minus delta A0 plus R sub A, delta sub AA. And we're going to have a better naming convention than this once we start getting a whole bunch of these things, because A's and B's and thetas are just going to be a mess. What we'll really do is we'll call this one like the, thank you, like the real loads, and we'll call this the case 1, we'll call this case 2, and then we can subscript with numbers where we're not limited by goofy things like this. Plus R sub A delta sub AA, that makes a part of your deflection go away. Cranking on this thing with the 1 times m sub A made some more of your deflection go away. Plus m sub A delta at A due to the moment at A is equal to 0. Then you'll say minus delta, it won't be a delta, will it? It was a minus theta at A due to the real loads, plus R sub A theta at A due to A, plus, that's R, that's R sub A, theta AA, plus M sub A, rotation at A due to a unit load at A. two equations and two unknowns. All of a sudden you can solve for the forces inside of a statically indeterminate structure. When I draw my shearing diagram, my beam will have this plus this on the left end for a moment. That'll be the initial moment at the wall. In this case, that'll be M sub A. That'll be his starting number. They'll both give you identical results. What else could you do? Well, we could grind this all kinds of ways, and I don't mind doing it a little bit. But after a while, pick one. I could, on my beam, take off the left moment, take off the left reaction, leave the support, but take off the left reaction moment. That's one. And take out the middle support. So this would be A vertical, A horizontal, Charlie vertical, and then B is right here. That is a good starting structure. Number one, it is stable. Number two, I can tell you how it deforms under the real loads. Number three, I can give you what they call a complementary solution. Put the unknown moment on the beam. Find out what it does to your beam. Causes a problem here. Causes that rotation. That's bad. Causes this deflection. That's bad. Come back and put a unit load on this one. You might put it down if you want to. We usually don't. We just usually point everything the same way. Let the minus signs take care of everything. And this. You know, of course, what we're going to finally do with those ones. And we're going to take that deflection and get rid of it with that times the reaction at B, plus that with the reaction at B. We'll have to watch out for your signs. So whatever structure that's statically stable that makes sense that you see first off, that's probably the best one to use for you. Anytime you got like a cantilever beam, that's always obviously pretty much a first choice. All the numbers usually work out simple. All right, sometimes you'll see them look like this. That's the same as this. It does look like the guy intends to really make the left end in the wall supported, 3 reactions, 1, 2, 3 at that support. Then this one here, this is a piece of a wide flange. It doesn't even look like they bolted it down. If this piece of steel gets hot, it'll just get longer and that wide flange will roll slightly like this. Won't hurt it. When it gets cold, it'll get straightened up again. Or a lot of times they will put a neoprene pad under there. It's the same thing. So even though this looks like a structural something, they don't mean that to be a pin. They mean for you to realize that's a single support. Reaction at B, A horizontal, A vertical, M sub A. Harrison, how many degrees indeterminate? 1 is correct. You make it into a cantilever beam by removing one support or one reaction. And if that's all it takes to get a nice stable structure that you can work from 305 only, then it's good to go. First degree. First degree indeterminate. Possible stable, statically determinate structures that you could lie that into. Most obvious one would be to just take off this support here. Also possible, you simply remove this moment at A and turn it into a simply supported beam with a reaction on the left, a reaction on the right. An undesired theta will result, which you will have to get rid of. Morales, how many degrees indeterminate? 1 degree. Dietz, how many degrees indeterminate? Dietz in here. Crawford? It is 1. You say, well, gee, this moment's all over, and there's things here, and there's walls over on the other end. You turn it into a cantilever beam. You have removed nothing but a vertical reaction. Therefore, it's indeterminate to the first degree. Probably the most obvious thing would be to turn it into a cantilever. Now, a cantilever would look like this. The moment would be here. It would distort the beam up. Will cause an undesired vertical deflection, which you would be required to get rid of. Yes, sir?
Why aren't the additional moments counted as another degree?
Well, because this, he didn't say it, but this is a known number. He just lists it as M, but he doesn't give you the number. This is 60 kilonewton meters. It's given. If a guy doesn't tell me how big the truck is, I can't design the beam. So he's got to give me the applied loads. How many degrees indeterminate? Getman?
Looks like 1.
I think you're right. That's why I always like your answers. I don't like your argumentative, and you're playing with my head, but I like your answers. Because what he looked at, he says, there's all kinds of junk over here trying to connect this thing down. But the truth is, no matter how hard they try, this structure is going to roll. That top angle is made out of relatively thin steel, and when that beam wants to roll, there's nobody in the world going to tell him he can't roll. That top piece is going to roll. When this bottom seat gets on that beam and that beam wants to roll, it's going to roll. It's just that simple. It just doesn't have the strength to do otherwise. The one in the middle here, it's just clamped to the web. There are no bending stresses in the web of a beam, and therefore you can't get any moment out of this bolt. And therefore this is meant to be and is a pin. It will take axial force nicely, and it will take vertical force nicely, but it won't take any rotation. The right-hand end, again, is nothing but this. It is statically determinate as is. No difference because of the load, first degree. Now then, here's a channel instead of a wide flange. Same idea. The channel will simply roll clockwise or counterclockwise, depending on if the beam gets hot or gets short, or if somebody puts some load on it and stretches it a little bit. It's not going to take any thrust down the axis of the beam. So there's a reaction at B. Does look like that he truly means that to be embedded into the wall as a fixed support. 1, 2, 3, 4, first degree. Maley? How many? Well, darned if I know. It looks like some kind of a post, but it's just bolted to the thing. So my guess is just like a something that'll keep it from moving to the left and right, but something that really probably won't stop it from rolling. And you know, I think we might have to go talk to the boss about this one. We really might. Yeah, talk to the boss and ask him what the devil this thing in the middle is. That's what you did. So you went and talked to the boss. Says, what's that in the middle? If this is really welded to a steel plate and the steel plate is embedded into some solid concrete and it's short and stubby, and if this is welded to the girder, this horizontal piece, then we might really say that is reasonably fixed. When you get in 446 and you do that, they'll give you factors that'll say, well, there's no such thing as perfectly fixed. Let's multiply it times some kind of a coefficient to make it kind of fixed. And that's what you'll do. Now, in this case, it really doesn't matter, because due to this moment, the thing comes up, but this is symmetric. There's 50 on both ends, and this is symmetric, so about this point, there is no slope. And so actually, we probably don't have to go talk to the boss. I would say that is no rotation at that point. I can also, if you want to, since it's symmetric, just go ahead and analyze half of it. And it becomes nothing more than a propped cantilever beam. No movement, no rotation due to symmetry, and no displacement. That's 4 unknowns. You got 3 equations of static, first degree. First off, I would say 1, 2, 3, 4, 5 minus 3 is 2, but that's not really right, because this little old thin clip angle in here, there's just no way it's going to stop it from rotating. If you didn't show that and he showed it embedded in the wall nicely, I'd say it's fixed. I say that's nothing but a simple support, a pin. I say that is a roller. I say that is a roller. Love, how many degrees? 1 degree.
Would you really say that's a pin, that little clip? Because if you put like shear on it, I would think.
Well, it's not a little clip. I mean, if someone chases you down the alley with it, you'll know it's not little. It probably weighs 8 pounds. And the truth is, your beam, I mean, he's just sketching here. The truth is, your beam is probably 24 inches deep, and the angle will be a 2 by 2 by 3/16 inch thick angle, and there'll be more bolts on it than that. There may be 2 rows of bolts on it. It's pretty good, but it really can't stop the thing from rolling. So all I'm trying to get across to you, though, really is what he means when he shows one of these. He means 2 supports, no rolling resistance.
For like in real applications.
I don't know much about that. Go ahead.
Like if you have something like that, and you put a moment on the end of the beam,
Yes.
wouldn't its ability to prevent rotation be the same as its ability to prevent shear? Because if you put a moment on those.
Let me refer you to your 446 prof, okay? Because they really will talk to you about the restraint such a thing causes with moment. I will tell you this is the way they're all made, and it has tremendous ability to take shear in the hundreds and hundreds of kips. All right, same idea. One support. One support, one support. If you say, well, I don't know why, if that's bolted tight enough, it wouldn't be a cantilever beam. That's what I built at my house. Well, okay, good luck. I think he means that to be a pin. I wouldn't put something like that on a quiz and then take off points if you didn't say it was a pin, because you could certainly argue, oh, wait a minute, I'm sorry, pin. Yeah, that's okay, but I need to show the force. Because if you say you think there's a moment on there, I couldn't hardly argue with that. I wouldn't put something like that. Degrees indeterminate. Green E. Where's green E? Okay. I know there's a green E and a green S. Green S. Really? Okay.
And those things hold tension, like at rollers?
Yes, they can take compression or tension.
And it's one.
It is one. That is correct. Because if you take out the middle, well, you don't want to take out the middle support, do you? If you take out the middle support, you don't have anything but two rollers, and then it's not stable. You could probably get away with that by just going ahead and saying, look, it's not going to move horizontally, and I'll take this horizontal capacity and pretend it's here. Take out the middle and let it deflect. That would be okay. You can get away with that for analysis purposes. Or you could just go ahead and take off one of the ends, in which case it would deflect like this. That would be the deflection at A due to the real loads on your new superstructure that can be analyzed, whereas the original one can't by itself, by statics. And then you get rid of this rotation, and you get rid of this deflection. No, you don't. You don't need to get rid of the rotation, do you? Sorry. The rotation was acceptable. Here was the original structure. The rotation was unknown and acceptable. So all you got to do is get rid of this deflection. Same idea. That means that, I promise you. There's one there and one there. 4 minus 3 is 1. Same idea. 1. Uh-oh. How many? 3 is correct. 1, 2, 3, 4, 5, 6. The truth is, I can give you the two axial. Since there's no loads in the axial direction, I can tell you these two. Unless it gets hot, then I'll have to go into thermal expansion. I can also tell you that these two moments are equal to each other, and these two shears are equal to each other due to symmetry. And that'll get you some down the road, but it is basically 3 degrees.
How would this thing fail if you were to increase that load?
The first thing that would happen is you'd form a plastic hinge. I'm not sure if it forms first at the center or the ends, but it would fail. You would see it look like this. It would also have some bending to it. But when this right here, that's the time to get out. That's the time to leave. All right, now we get something with some meat on its bones. Well, you're not going to be happy about it anyway, so thank you, though. 1, very good. 1 is correct, because this guy just can't take any horizontal force, not across his web like that. He's just too skinny. Number 2, he can't stop it from rotating because the web is too skinny, and therefore this is basically nothing more than a single roller support. Then it would be your job to turn it into a structure that has nothing but that on it. And then it would be your job, and this is getting to be a little interesting now, to draw the moment diagram due to the real loads. See how 6 times 1 foot is 6, times 2 foot is 12, times 8 feet. And to draw the moment diagram for the vertical member, and that's what you would call M0. That'd be the moment diagram due to the real loads. And if you don't see where this piece right here came from, then you'll need some practice, because 6 times 8 goes here, 6 times 8 goes here, 6 times 8 goes here, goes here, goes here, goes here. It's the same all the way down. And the deflected shape for the structure with those moments on it looks like this. You'll notice how I showed this point at the same height as it used to be. I'm ignoring what slight axial compression there is in the member. You'll notice I drew that as a very good 90 degrees at the angle. You'll notice I'm bending it a lot, bending it a lot, bending it a little, bending it just a little, bending it none. And now it's straight, because there's no moment out here. There's your distorted member. It has, sadly, a downward deformation, deflection at A due to the real loads. It'll be your job to come back in and get rid of them. Here is your structure without the loads shown on it. Here's where your problem is. Here's a 1. Here is the moment diagram. 1 times 1, 1 times 2, 1 times 5, 1 times 12, 1 times 15, 1 times 16. And here's what the moment diagram looks like on that piece here. That will be a little moment diagram due to unit load at A. You'll be using these moment diagrams to solve for the deflections. Here's the deflected shape. This is the deflection at A due to a unit load at A. And we will spend half the class learning how to calculate these deflections so that you can write the following equation. The minus the deflection at A due to the real loads plus R sub A times delta A at A equals 0. That would be your job, to make this deflection on the structure you decided to draw because you couldn't analyze the real structure and did some ugly things. You got rid of them. All right. Got any questions? Stick around. A web of a beam. You have a wide flange